Hey, my name is Tiago, and I'll present this week's SIGTYP lecture. The title of this talk is an informative exploration of the lexicon. I'm a second-year PhD student at the University of Cambridge, where I'm advised by both Simone Teufel and Brian Cottrell. So this talk will be mainly divided into 4 parts, and each of them roughly corresponds to a paper, or in the case of the third one, it's 2 papers merged together because they have a unifying topic. And here are some spoilers of the results I'll talk about. So in the first paper I'll talk about, we use bits per phoneme as a measure of phonotactic complexity, and we find that it has robust trade-offs with word length. So you can see this in this plot where each dot is a language, and you can see there's a strong correlation between the cross entropy per language and the average length in each language as well. And the second paper, we analyze bits per phoneme and the first and in the second halves of the words, and we find a cross-linguistic tendency to front-load information. So you can again see it in this plot, where the fact that most languages are below this identity gray line means that the initial part of the word surprisal is larger than the final part. In the third one, we operationalized systematicity of the sign as a mutual information between word forms and meanings. And we found small but significant values both within and across languages. So this was trying to quantify the systematicity of the sign and non-arbitrary form meaning associations across languages. So these are the 2 tables represented here. And then the last one, we operationalized lexical ambiguity as a conditional entropy of the meaning of the meanings a word can take given this word. And we found consistent trade-offs with the word's contextual entropy. So this is again represented in these plots. But in these plots, each dot is a word in the language instead of a language itself. So the unifying theme across all these 4 results is using information theory to define linguistic concepts or ideas, and using these operationalizations as a way to measure these properties in natural corpora and trying to answer linguistics questions this way. So I'll start with this first part, which is called Phonotactic Complexity and its Trade-offs. This was joint work with Brian Rourke and Ryan Cottrell, and this paper was accepted at TACO in 2020. So Phonotactics defines this set of sequences of speech sounds that are allowed in a language. So, for instance, in English, the word brick exists and is kind of a good one. It sounds English and it sounds right in the language. The non-word blick does not exist, but it could. Like most English speakers would say that that is a good word form. It just happens to be unused, but it couldn't easily be a word. And Benek does not sound English. It either sounds foreigner or maybe misspelled or mispronounced, but it doesn't sound like it belongs in the English vocabulary. And this is not just a property of English. Every language will have this set of words that sound natural in it, or that do not. The compensation hypothesis will be one of the main themes of this paper, and to talk about this compensation hypothesis, I first need to talk about the equal complexity hypothesis, which is something that several linguists still believe in, and that came about like I'm not sure in the last century, but that a lot of linguists believe that all languages are roughly equally complex. And as a consequence of this belief, if we believe in that, we need to believe that compensatory relationships must arise from different complexity measures, because we know languages are not equally complex in each axis of complexity. For example, a language can be more morphologically complex than another, but compensatory relationships should arise between them. So one example of this is that languages with larger vowel inventory sizes usually have shorter words. So over the years, several measures of phonological complexity have been proposed. The most simple ones are the size of phoneme inventory. So like I said before, the number of vowel categories allowed in the language. One step above this would be the markedness in these phoneme inventories. So for example, some linguists have claimed that clicks are more complex than other phonemes. And because of that, languages that include them should be counted as more complex. And if you want to go one step above and consider larger linguistic units, you could count the number of listed syllables, since not every pair of phonemes is allowed. And most of the work that has looked at this phonological complexity measures have taken word length implicitly into account as another complexity measure, since they usually look at trade-offs between these phonological complexities and the word length itself. So in this work, we want to look at phonotatic complexity, and we defined it as the bits per phoneme in a language, which is basically the entropy of that language's word types. So this is very easy to estimate. We just need any character level language model. And by taking its cross entropy on a set of held out word forms, we can get an upper bound for this entropy. The trick is that the better this language model we get, the tighter this upper bound will be. So in this work, we looked at both trigrams and character level LSTMs, and we analyzed both of their cross entropy as a proxy for this entropy that we wanted to look at. So the rationale behind using this bit per phoneme complexity measure is that it requires very modest linguistic annotation. We only need word lists in the analyzed languages and annotated in a unified phonetic alphabet. So for example, in IPA. This complexity metric incorporates frequency of phenomena. So for example, in English, most speakers will have the sound h in their vocabulary, since it's present in words like Bach, for example. But it's a very rare phoneme, so maybe it shouldn't be taken into account as much as other ones. It captures interactions between phonemes and long distance dependencies. So it will capture both the number of syllable structures that the language allows, and long distance dependencies like vowel harmony, for example, which will make a language less complex according to our metric, because the words will be more predictable. For our analysis, we looked at this data set called North-Eurolex, which is composed of a bit over 1,000 concepts in 107 languages. And all of these concepts are aligned across languages and annotated in IPA. These concepts are also what they call basic concepts, and they will be, for example, body parts or flora and fauna that are commonly found in a lot of the world's languages. And in this sense, most, although not all, of these words will be monomorphic in a lot of the languages. So in a sense, it roughly controls for the morphology of the languages as well. And this data set spans over 21 language families from Europe and Asia. And as a side note, we omitted Mandarin from our analysis since there was no tone annotation. So it was underspecified here. When we look at the correlations with the classic measures of phonological complexity, the ones using inventory size, we see that the correlations are either not there or very weak. For example, if we look at the vowel inventory size, there is a very weak correlation there with the average word length across languages. But when we look at bits per phoneme, even with a unigram language model, we already have a stronger correlation than with the phonological measures. But we also see that the better the model we use, the stronger the correlations we find. And more specifically, when we look at the LSTM, we find very strong correlations of above 0.7. This here is a plot of both the LSTM and the trigram results. And we can see again that the correlations are very strong. This trade-off between cross-entropy and average word length across languages. These results could, though, arise for other reasons that are not that interesting. So, for example, there could be positional effects that we're not considering, and that could be driving the results. So, for example, this Van Sol and Paul's paper from 2003 showed that phonemes later in a word in general have higher probability given the previous ones than the earlier ones in context. So since longer words contain more later phonemes, they naturally would have lower cross entropy. So to control for this, we truncated words and consider only the first 3 characters in each word form. And took the correlation between this, the cross entropy taken in these truncated words versus the average full word lengths across languages. And while the original correlation was a bit below 0.7, negative 0.7, the truncated one is at roughly 0.45. So we see that although some of the effect is in fact a result of these positional confounds, most of the effect is still there when we control for it. In the paper, we have other confound analysis if people are interested. But another thing that we looked at was, and we analyzed these results both inside and across language families. So the classical measures of phonological complexity present stronger correlations when we average them per language family and then take the correlations across the families. But they do not show the same correlations when we look inside the language families themselves. When we look at bits per phoneme, though, we still find strong correlations in both cases, suggesting this is a more robust way of analyzing this complexity trade-off. I'll finish with this first part now, but in the last part, I'll have a quick run back to these results and analyze all the four topics together. So see you in part 2.